Hi folks, welcome to lecture 9, and in this lecture we're going to take a look at reciprocal functions. But first we're going to take a look at the more general rational function. So a rational function is a ratio of two polynomials. Now that sounds very complicated, but it's really where we have a polynomial is something like this. So this is a polynomial in X. It's got many terms, as in more than one, and this is also a polynomial. So that's what that's what a rational function is. It's where two of those are divided. It's rational because one is divided by the other, like a ratio when we're comparing things. The polynomial we can't divide by cannot be zero. I hope that made sense. So same as with our fractions, we have a numerator, we have a denominator, but essentially all the rules of fractions apply, but all the rules of algebra also apply. So rational functions, when you see them, you need to kind of take a good bit of care. In this module though, we'll be kind of analysing a simpler type of function, similar and simpler, the reciprocal function. So the reciprocal function is given by 1 over x. Now it can be written in loads of different ways, as we'll see. 3 over, sorry, that wouldn't make sense. 3 over 4x, anything like that. The main way you know a reciprocal function is the variable is on the bottom. It's on the denominator. Remember from our rules of powers, anything that lives below the line can be written with a negative power. If this was x squared on the bottom, this would be x to the power of minus 2. It's very important to get familiar with this kind of relationship at this stage. The graph of this function is called the hyperbola, and it looks like this. Now, just to try and give you an idea where a hyperbola comes from, it's called a conic section. So a circle is actually a conic section if we cut the top off it. An ellipse is if we cut the top off at an angle. Here's our parabola. How you know a parabola? It's kind of as if the cut is parallel with the cone. And then a hyperbola is where we cut straight down. We cut vertically. Imagine that's like a knife. And this gives us our hyperbolic shape. One way though is there's one way to differentiate it from the parabola. Well, there's a couple of ways. Is there's usually a pair of curves, the top and bottom of the conic section, and they're like kind of bows, as in the ends travel away to infinity and away from each other. And that's how you know you're dealing with a hyperbolic function. So like infinite bows, I'm kind of talking about bows and arrows. That kind of an idea. So just take a look at reciprocals in kind of a more formal sense. We introduced these last semester. So to get the reciprocal of a number, divide 1 by the number. So the reciprocal of 7 is 1 over 7. The reciprocal of n is 1 over n. So here we have some numbers and their reciprocals. To get the reciprocal of a fraction, simply turn it upside down. Remember, say if we had 2 over 3, its reciprocal is 1 over 2 over 3. Using our rules of fractions, flip the lower one and multiply. But it's just as quick to flip it upside down. Make sure you keep any sign. If this is negative, its reciprocal is still going to be negative. Don't be tempted to change the sign. You're thinking of something different from the leave insert, which doesn't apply here. You're thinking of a negative slope, but it's another story for another day. So here we have a term and here's its reciprocal. If we get the reciprocal of this new term, we end up back where we started. So here we can see in the table, one way to think of anything just to make it easy with reciprocals is 2x can be written as 2x over 1. So then when we get its reciprocal, we simply flip it upside down. The reciprocal of this, so this is a rational function because it's a polynomial in x over another polynomial. Well, it don't have to be an x, but two polynomials written as a ratio or as a fraction. This is kind of called a ratio as well. I know this is also another way of writing a ratio. Ratios can be written in lots of different ways, not just with the two dots. I think we introduced that when we were discussing ratios back in semester 1. So how do we recognize a reciprocal function? So when the fraction looks like a function and the input is part of the bottom bit. So the input is what we kind of feed into the function. So this is a reciprocal function. This is another one. This is a more complicated one, but again, A is in kind of the reciprocal position. We'll talk about this in a little bit. And here we have, this is actually Boyle's law, but here V is an input and it's on the bottom. So V has a reciprocal relationship with P. That's how we'd write it. Just to be clear then as well, P has a linear relationship with T. If we double the temperature, that's going to double the pressure. We'll talk about how a reciprocal relationship works in the next slides. In a reciprocal function, the power on the input is negative, so this last thing could be written like that, this one. So the simplest reciprocal equation can be written like this. And then there's the general reciprocal equation, which has the A, B, and C constants. We'll be working with this in the next lecture. So just make sure you're familiar with it, because you'd be expected to kind of use it. So unlike the previous functions, linear, quadratic, and cubic, reciprocal functions are not continuous. Continuous means that for every input there's an output, so there's no breaks in the line. This is what a typical hyperbola looks like, a reciprocal curve. And there's this weird thing going on here. So essentially a reciprocal functions, because we have y is equal to 1 over x, when x is equal to 0, we now end up in this scenario. And this is like a mathematical black hole. This doesn't exist. It's not defined. It cannot be drawn on a graph. And essentially it literally is like a black hole. It's kind of the zone where maths can't go. Now you can get very, very close to the center of the black hole, but you cannot get into the black hole, so to speak. So some mathematicians kind of devote their lives to kind of trundling off to this kind of mathematical murder. We don't have to do that, thankfully, and we kind of use the knowledge gained on their travels to help us with kind of more complex maths. But essentially, this black hole is what actually defines the curve. That's what gives us that unusual shape. Now, we're not going to get into this in any depth at all, guys. We're just going to have a quick fly through, so don't worry about it. But I hope you'll kind of see that there is a whole world of mathematics in exploring what's going on very close to here. So asymptotes are essentially like an imaginary pair of lines which bisect that mathematical black hole. Wherever your function is going to return a 0 on the bottom, that's where you're going to get one of these black holes, because this type of thing cannot be defined. Anything divided by 0 cannot be defined Because the question you're asking is how many zeros is there in 10? There is no answer. So this is how our asymptotes appear. So this is called the vertical asymptote, and it's essentially a line you could draw through that black hole, but the curve would never touch it. The blue line, in theory, in reality, would never touch the dotted line. Now, I'm using a package with very limited kind of graphics ability, so it looks like they're touching, but mathematically, they don't touch. So this asymptote, as it's called, this is the vertical asymptote, and in this case, it appears that x is equal to 0. That's the equation of that line, that dotted line. There's also a horizontal asymptote, and this crosses where y is equal to 0. And like I said, the asymptotes kind of bisect that black hole, the mathematical black hole, where we end up with 1 over 0. Sorry, there's the vertical asymptote appearing. Yeah, and so that's the equation of the vertical asymptote, and it appears where y is equal to 1 over 0. Horizontal asymptote occurs where x is equal to 1 over 0. And that's, if we manipulate that equation, y is equal to 1 over x, we could manipulate it and we'd end up with x is equal to 1 over y. And that's what we're exploring here. That's what gives us our horizontal asymptote. I'm not going to get too into explaining it, guys, because really all you need to do is just try and figure out from the curve where do these lines appear. It's usually fairly obvious. So the position of a reciprocal curve is determined by these asymptotes. But the shape is nearly always the same. So it's nearly always that shape. And then in the real world, we only tend to deal with this part of it, because in the real world we're looking at radiuses and volumes and lengths. They're all positive values. You can't have such a thing as a negative volume, or I was going to say negative pressure, but you can't have negative pressure. So, but in general, we only, as scientists, we tend to deal with that part of the curve. Mathematicians deal with this part of the curve, and that's what you'd be studying if you were kind of in Cork or Dublin doing maths. So the main thing to realize here, and this is the most important part about reciprocal functions, as my input gets bigger, so as I head along this direction, as x gets bigger, my output gets smaller. I hope you'll agree with that. When x was very small, y was very big. It was way up, like infinitely high. As you get infinitely close to 0, your y value gets close to infinity in value. So as the x gets bigger, the y, we can see the y starts at the top and literally drops in value and then slowly keeps dropping. So as x gets bigger, y gets smaller. And that's the most important thing to realize. Just to give you a few examples, kind of say if we had y is equal to 1 over x, I'm just going to make x bigger. When x is equal to 10, y is equal to 1 over 10. When x is equal to 100, so x is getting bigger, y is getting smaller. When x is 1,000,000, y is 1 over 1,000,000, which is 0.000001. So that's what I'm saying. You can see here our x values are getting bigger. I don't like the way they're going, getting bigger as they go down, but the y values are getting smaller. And that's the main thing, that's the main feature of a reciprocal function, is that when you increase your input, your output decreases. Just taking a look at some of these reciprocal functions in real life. So as I was saying, these are the ones, sorry, I thought I was on a different slide. These are the ones you're going to meet in the real world, as I discussed on a previous slide. So this is important. Now, in a proportional reciprocal function, there's only one term on the input side. So here we have one term. If it was written y is equal to 5 over x plus 7, now it's got two terms. Now it's got three terms. So each term could have 4 or 5 bits in it, but each term is separated by a plus or minus or an equal sign. That's how you know a term. So here's an equation with 4 terms. Luckily, most of the reciprocal functions we're going to be dealing with only have one term, which makes the maths a good bit simpler. So there's one term and one input. It's really important to get those kind of things sorted in your head. Remember, in an experiment, and the input is what you change. So here we're looking at period on the bottom and frequency. So as we change the period, say of a pendulum, the frequency of it changes. And as we make the period bigger, if that increases, then our output decreases. So here we have one term and one input. This is a more complex problem. This is about the resistivity of a wire, and it simply says the resistivity of a wire depends on 3 inputs: the density of the wire, the length of the wire, and its cross-sectional area. That's what's on the bottom. So density and length are both linearly related. So if we double the density of the wire, that'll double the resistivity. If we double the length of the wire, that's also a linear relationship, then the resistivity is doubled. Ordo is proportional to 1 over A. So if we make the area bigger, the resistivity of the wire decreases. And that makes sense, because the bigger the wire is, the more room there is for current to flow. More current can flow, and that's the opposite to resistivity. So with those 3 things, this is why, now they're not so popular now, but tungsten bulbs used to be the most common bulbs. Now they're not very environmentally friendly, but they all depended simply on those 3 relationships. They were very long. That's why they were curly. This was to maximize the resistivity. In other words, to maximize the light. The more resistant the wire is to electricity, the brighter it is. The density was important, so this is why they often use tungsten, one of the most dense metals kind of commercially available. And then finally, the cross-sectional area, that little filament as it was called, was very, very thin, very, very long, and very, very dense. And the more we could increase those things, the smaller we could make A. If A decreased, then R increases, and the brightness of the bulb increases as well. So that's really what I'm trying to teach you on this module, is to be able to look at a function and kind of go, oh, okay, there's 3 things going on here. 2 of them are linear, 1 of them is reciprocal. And you'll start to, even just by looking at it, know, well, if I change this input, A, okay, that's going to have this kind of a impact on my output. That's called science, being able to kind of predict and then measure what happens when I change something. This is Boyle's law. I've just written it so you might know it as PV is equal to nRT. Here we have one term. There's three inputs: N, the molarity, T, the temperature, and V, the volume. And then R is a constant. So just to explain this, we're saying P and V have a reciprocal relationship. If I make V bigger, if I double the size of the balloon, we can see at 1 meter cubed, the pressure in the balloon is 8 bar. If I double the size of that same balloon, that halves the pressure. And that's because we have one term on each side. If there was a few terms, then there would be a reciprocal relationship. One would get bigger as the other got smaller, but it'd be a little bit more complicated than this simple kind of relationship I'm writing here. So in a reciprocal function, the input, if the input gets bigger, the output gets smaller. That's kind of a general case. But when we're dealing with these nice simple reciprocal functions, then it's more specific. That's a proportional reciprocal function. And we get, if the input is doubled, like here, I doubled my volume. As a result, so this got bigger. My input, my output got smaller. And that's the most important thing to remember about reciprocal functions. Just taking a look at Boyle's law, we'll look at it in a little bit more detail in the next lecture. But pressure and volume have a reciprocal relationship, just like I was saying. This symbol here that means proportional. And you just treat it like an equal sign. And this is a graph of Boyle's law. We can see the volume getting bigger. As the volume goes this way, the pressure goes down. Speed and time. Most people are kind of aware of this, but they wouldn't formally call it a reciprocal relationship. So for a fixed distance, if you were driving to Dublin, say 200 miles, time and speed have a reciprocal relationship. Now, you can't control time. The only thing you can control on the journey is your speed. So that's your input. So if you double the speed, say if it took 2 hours to get to Dublin at 100 miles an hour, I think it'd be obvious to most people, if you doubled your speed, obviously now this is not, I'm not suggesting you do this, if you doubled your speed to 200 miles an hour, well then you would expect, we'd go from here, sorry, that should be up there, I was wondering why it was to 1 hour here. If we doubled our speed again, or if we went to say 300, again this would now be, if we could increase again, say to 400 miles per hour, now it would only take half an hour to get to Dublin. And that's the idea. When we increase the input, the output decreases. One thing to note here, and it's kind of not very common, but time is on the output axis in this case. So time and speed have a proportional relationship. Doubling the speed halves the time taken for a journey. Half the speed doubles the time taken for a journey. So you kind of intuitively know this, but you wouldn't recognize it as a reciprocal relationship. So there's just saying time is an output. Satellites. So a gravitational slingshot is governed by a hyperbola. And they use kind of, if you're wanting to kind of design rockets and stuff, you're going to be dealing with hyperbolic functions in a big way if you want to make sure that your satellite gets to where it needs to. Because it's going to be passing into the gravity fields of various planets. So, and that's going to have this parabolic shift in direction. So nearly all lenses you use are hyperbolic. This is just a little bit about the physics of it. So essentially you need a focus point, and that's the difference, guys, between a parabola, remember the quadratic curve, and a hyperbola. I'll just write one a little bit more. Is a hyperbola has a focus point, and that's why they're used for lenses. A parabola, the quadratic curve, doesn't. I should really write that a little bit on the side as it should be if I'm talking about 1 over x. But again, it still has a focus point. So when it's that focal point, focal length is based on then that's how the lens is designed. Not so much used now, but in the Second World War, parabolas were used, or sorry, hyperbolas were used for radio signals. And this LORANS was developed, long range navigational systems. It's been superseded now a lot by GPS, but this was how most people navigated pretty much for about 70 years. It's all to do with radio waves and the way two intersecting radio waves, so there's two bases. And they kind of, they produce radio waves travel in hyperbolic, well, they travel in circles, but where they meet then produces these hyperbolic patterns. It's a little bit beyond me, I have to be honest. I just know those are hyperbolic shapes. Just a few other places where they appear. We're nearly finished now. In gear trains. So here, this could be the drive shaft. But it's trying to turn a wheel at an angle, or trying to turn a motor, trying to turn something else at an angle. Hyperbolic gears are used for that. There's lots of different ways. If you needed to go just at right angles, there's a few different ways that will get you there. But when you need to go off at an angle from the main drive shaft, that's where you'd use a hyperbolic gear train. Industrial cooling towers. These sides are hyperbolic in shape, so they're governed by the functions we were discussing. And the reason for that is it's the most efficient way of accelerating the gases. It gives the gases the most acceleration to get them right good up high into the atmosphere. Unfortunately, we don't think along those lines as much anymore. These are cooling towers though, so really what they're ejecting is water. So you'd see loads of what looks like smoke coming out, but it's actually just steam, usually off nuclear reactors. The light shadow from a torch or a lamp is hyperbolic in shape. Don't know how to use that in any kind of a practical scenario, but I just found it, so I said I'd include it. So that finishes us up for there, guys. So thanks for listening. We'll chat again for the next lecture.